Hello everyone, and welcome to today's webinar, Designing, Building, and Testing UAVs. This webinar is brought to you by our sponsor, Spectracom. I'm Kelly Limpert from North Coast Media, and I will be your event manager today. Before we begin, I'm going to go over some ways that you can participate during today's presentation. Although you are currently in a listen-only mode, we encourage you to ask questions throughout the presentation. Just type in the Q&A box at the bottom left, then click Submit to place your question in queue. You can also submit questions via Twitter by using the hashtag GPSwebinar. Questions that were submitted during registration have already gone to our speakers and may be answered in this webinar. If you experience any technical difficulties during today's event, use the same text box at the bottom left to tell us about your issue, and assistant producer Bethany Chambers or I will personally assist you. Finally, a recording of this webinar will be available tomorrow afternoon at gpsworld.com/webinars. A link to the on-demand recording will also be emailed to you when it's available. If you have any colleagues who couldn't make it today and you'd like to share this webinar with them, you can do so at any time via the social media links on your screen. Now, I'd like to turn today's event over to our moderator, GPS World Editor-in-Chief, Alan Cameron.
Thank you, Kelly, and welcome to everyone out there. Good morning to you if, like me, you're in the Pacific zone of the United States. Good evening if, like three of our speakers, you are listening in from Europe. And welcome to everyone from around the world. This is the first of two webinars we're having on UAVs this fall or this winter. Today's is design-oriented, design, build, and test of UAVs. In another month, on December 17th, we will have a second webinar relating to the use of UAVs in the field, Introduction to Survey and Mapping with UAVs. I can see from looking over the list of attendees today that we have a number of UAV designers or would-be UAV designers. I can certainly see that from the questions that have been coming in. So we have a content-rich, design-oriented design and test webinar for you today, and December's will be more user-oriented. Before we begin, I want to thank again our sponsor for this webinar, Spectracom. Spectracom is a collaborative partner to customers requiring fail-safe positioning, navigation, and timing solutions with a broad portfolio of GNSS-based synchronization, simulation, and test products, and a rich heritage in supporting mission-critical applications. Spectracom is uniquely qualified to support today's challenges in deploying PNT in dynamic UAV, UAS environments. As I said, we have three speakers from Europe and one from the U.S. today. This is partly by accident, but partly by just the current UAV climate. There is a lot of UAV activity in Europe, at least from a number of independent efforts. There's significant UAV effort in the U.S. as well, obviously. I can tell you before we begin, I see a lot of questions coming in asking about FAA regulations and in the U.S. governing UAVs. I hate to disappoint those people, but we are not going to be covering those. We're not political specialists. We're not regulation specialists. We are presenting this from a design and engineering point of view. So today we have Lasse Klingbeil from the University of Bonn. We have Jeffrey Fayman from Geodetics in California. We have Florent Hennart from Airbus in France, and Jan van Hees from Septentrio in Belgium. Each of them is going to give you a detailed close-up look at some aspect of UAVs in actual design and operation. And we'll turn first to Lasse Klingbeil from the Institute of Geodesy and Geoinformation at the University of Bonn. Lasse, the floor is yours.
Hello. Hello, everyone. This is Lasse. Thank you, Alan, for the introduction. I will tell you about our development of a light-weight direct georeference system for UAVs, for small and light-weight UAVs, I have to say, which is below 5 kilograms, which is an important threshold in Germany. And I haven't done that alone, of course. I'm from the chair of Geodesy at the Institute of Geodesy and Geoinformation at the University of Bonn. And what we do is somehow all related to this talk. We do GNSS antenna calibration. We do mobile mapping with various platforms. So we basically move laser scanners around and cameras and see what we can do with them. And we also do multi-sensor data fusion, so meaning that we develop the algorithms to fuse GNSS, IMU, and other sensors for the purpose of mobile mapping. On the other hand, we do terrestrial laser scanning, information analysis, for example, so based on the data we take with the scans or with the mobile mapping. And we also have some people working on closer range laser scanning, mainly in the area of plant phenotyping. As a motivation, I want to say that if you walk through the Intergeo over the last few years, you see that there are a lot of two things which have become very popular. One of them is mobile mapping in general, and the other one is UAVs. So the mobile mapping part, so the state of the art is we have these large and heavy systems. They have a GNSS IMU for post-processing and for the direct georeferencing of the laser scanner data. So these systems are used to synchronize the laser, the GNSS, and potentially images. And in post-processing, they're very accurate to get nice point clouds. And on the other hand, we have the UAVs, which have become very popular, and they are small and lightweight. They also use GPS, but usually only for the waypoint flights. And then you have some offline bundle adjustment software, which generates nice point clouds. And this has become very popular in the last years, and there's nice software available. And the georeferencing in this case is usually done with ground control points. So our question was, is there something in between these two things, which maybe a direct georeferencing system, as is IMU is usually on these mobile mapping systems, which is light and flyable, basically. You can put it on a UAV, which gives you absolute accurate precisions, can trigger and synchronize other sensors, and which gives you this data in real time, in hard real time. So you can even use it for navigation. And with this system, you could do like direct georeferencing of aerial images. You could do high precision navigation in autonomous flight, and you could do other nice things like portable and small mobile mapping systems. And when we started to develop this unit, there was actually nothing available like this. Now this changed. So as we may see in the last talk today, which has a similar goal. This is a system we developed. So it's based on a dual frequency GNSS receiver. It has a single frequency GNSS receiver. This is to build a small, short baseline on the UAV. We have the usual 3-axis gyroscopes, accelerometers, magnetometers, a barometer, a radio module, which is important to get the reference, so the GNSS data from the master station on the ground in real time, and we have the interface to other sensors. And the whole thing is just 10 by 11 by 5 centimeters as a size, and the weight is below 400 grams, including the GNSS antennas. And we did all this algorithm development in-house to be sure that we have basically everything under control. So there are some commercially available units with similar or partly having these specifications, but we don't really know what we have there. So we decided to do it by ourselves, especially the algorithms. And we are very high flexible and doing it like this. So the accuracies are below let's say around 1 centimeter and below a degree in ideal GNSS conditions. This is maybe a bit too detailed. I will quickly go through that. So we have this module, and the module has a real-time processor, so a real-time operating system running on a small processor, and we have an FPGA which parallelize the data very quickly. And then we have few tasks running, which is the RTK GPS solution algorithm. We have the GPS attitude, which is processing the baseline data. And we have the integration of the whole thing using filters. And we have spent some time to do a fast ambiguity resolution, because this is very important, especially when you fly next to buildings and below trees, which is one of the goals we had. So if you lose track of satellites, then you have to do the ambiguity resolution again. And we spent some time on optimizing that to be able to do that within one measurement epoch. So this is a UAV which we built around this system, let's say. So it's based on a microcopter UAV. We have two GNSS antennas, which you can see here. We have the georeferencing system, which I managed, which I've mentioned, which is in the middle. We have a PC board, and you can also see that we have stereo camera systems, which is later used to combine it with the GNSS for a better trajectory estimation. I think we will hear about these things in the next talk. I'm not sure, in the second last probably. And this is a UAV we built, and I want to show you some results of what we did. So let me explain a little bit what you see here. So we flew with this UAV. We had 4 independent flights, as you can see here on the upper left corner. And what we did during this flight, we took images with a camera at 1 hertz, with a 5-megapixel camera. We in real time tagged these images using the RTK GPS and the orientation from our system. We sent this back to ground, and on the ground there was a bundle adjustment, basically not really in real time, but in near real time. It was processing the data, so that you can see during the flight already the point cloud building up, and they're all georeferenced. So each of the points has actually a global coordinate, and you can see that because we just threw all 4 clouds of the 4 flights into one bucket, let's say, and you see that they fit together. You can't even see where the 4 clouds are. So there's one border is actually going through the house, but you nearly see it. So it shows that the georeferencing is working. And you see the accuracy. We compare it with a TLS, with a terrestrial laser scanner point cloud, and we see that most of the points are below 5 centimeter accurate. So this is the absolute accuracy of this method. We have another application. Now I skip that because I'm out of time. This is about the camera integration. We have another application, which is precision farming. So what we did here is we flew over a field trial with wheat, I guess. And we had 2 different flights with 2 weeks apart. And we just calculated the cloud and calculated the difference of the clouds, which we did without any ground control points, because we had this nice georeferencing unit. And then we can just basically calculate growth rates. If we do that more often, we can calculate how fast, which sort, which genotype of the field trial is doing well, let's say. And you can do that with an easy flight. It takes 5 minutes, and then you calculate a few hours, and you can get these little nice diagrams. And another thing is this: we put our system, our georeferencing system, together with a little scanner, with a very lightweight and small, not so accurate, but small and lightweight scanner, and we can easily use this to directly georeference the scanner data. So you see this building here, and this building is the measurement time was probably 3 minutes just walking past this thing. And there's, without any post-processing, there is a direct output of the georeference point cloud. And this is a nice thing you can do if you have this this little unit, then you don't need any ground control points for that. And with this nice picture of this, it's actually a castle in Bonn. It's very nice. I want to close my talk and thank you for your attention.
Thank you very much, Lasse. We're going to come at the same subject or a similar subject or a closely related one from a slightly different angle, sort of like an independent UAV flight. We're going to be flying over this subject area and taking different viewpoints. So for the next one, we turn to Jeff Fayman from Geodetics in San Diego. Go ahead, Jeff.
Alan, thank you for the introduction, and that was very interesting talk from Lasse. Very interesting indeed. My name is Jeff Fayman. I'm with Geodetics. We're in Southern California, so it's early for us compared to some of our colleagues in Europe. I'm going to talk to you about a related subject to what we just heard. We call it, the title of our presentation is Geopointing of Onboard Sensors on Small UAVs for Real-Time Mobile Mapping Applications. So what I want to convey is that the short period of time that we have here to present this material doesn't lend us to be able to go deeply into any of these topics, but I do have references at the end of the presentation for papers that were published that do go into that level of detail, and I invite you all to, or those that are interested, to go ahead and get access to those papers, and you can get more details. And we're going to give an overview of the work that we're doing here at Geodetics in these slides. So our goal is what we call perception of the environment. And that's sort of a high-level capability that we're looking at applying our technologies to. Things that we fall under a perception of environment include sense and avoid, collaborative navigation, terrain-aided navigation, and mobile mapping, which is related to the previous topic that we discussed. Now, these high-level perception of environment capabilities are really built up of lower-level building blocks. So in order to perceive the environment, we need to be able to directly georeference the sensor data, as Lasse talked about. And that, in turn, requires us to be able to geopoint our sensors. And that's going to be these two topics, sensor geopointing and direct georeferencing of the sensor data, are going to be the two subjects that we discuss in our presentation here. So let's focus first on geopointing. This is an underlying capability that you need in order to achieve the higher level functionality. So in our work here at Geodetics, we do both civilian and military applications, and you can see various platforms that we come across in our work. Some of them are large, some of them are small, some of them move fast, some of them don't move at all, some of them move very slowly. So there's a whole range of different platforms that we come across, but the commonality is that each one of these platforms has a sensor suite, and you need to be able to geopoint the sensors in the sensor suite. Traditionally, geopointing has been achieved with either a multi-antenna GPS solution, interferometry, or an inertial navigation solution with an IMU. And when you consider both of those approaches and the various size and dynamics of the platforms that these geopointing technologies get applied to, you end up with a trade-off. And the trade-off is between the size of the platform and the antenna separation that you're able to put on for the multi-antenna system, the dynamics of the platform, whether it's stationary or dynamic, and in the case of an inertial solution, the quality of the IMU. So there's quite a few parameters that come into play here. And in our work, we find that sometimes you end up in a situation where you can't apply a straightforward implementation of a multi-antenna solution or an inertial solution. Sometimes things just don't lend themselves easily to either one of those approaches. And so we look at ways that we can optimize and combine technologies to be able to address those situations where one or the other technologies alone won't be able to achieve the results that you're looking for geopointing. So I'm going to talk about two cases that have come across our work here at Geodetics and show you how we've addressed those subjects. So the first case is a challenging case, a small stationary platform. This is a case of a mast that's on a moving vehicle, in this case the tank. And at the top of the mast we have a sensor suite. This is several different sensors, and we need to be able to know their geopointing information. Now the problem here is that the top of the mast is not large enough to contain or to hold a pair of GPS antennas to use the multi-antenna approach to doing the geopointing. And the other problem from an IMU perspective is that this is a stationary platform, so it's not moving. And they'd like to be able to turn the system on and know the heading or geopointing information as fast as possible. And they may not have a lot of time to sit stationary in order for your filters to converge. So the problem that you can see with the IMU approach, well, the problem with the multi-antenna approach is that there's not enough room to put it, so you can't use it. And the problem with the IMU approach is the amount of time it takes when you turn the system on in a stationary environment for the filters to converge. And you can see for a couple of IMUs that we work with what that convergence time is. It could be quite lengthy. So we looked at this problem and we said, what can we actually do to improve the performance here and actually provide a solution to this? And our approach is to look at it from an algorithmic point of view. And we developed a couple of algorithms that we applied to this. A modified course alignment algorithm, which allows us to provide a course alignment good to about 1/2 degree. And then once we have that information, we move into a modified fine alignment, which provides us a faster convergence time. So for this particular IMU, the KVH that you see the results for, 30 minutes of convergence time without the algorithms gets reduced with the algorithms down to 10 minutes. So it's a fairly significant improvement in convergence time. And for the particular application that we have shown here, that met the requirements for the customer. They were able to turn the system on and actually could wait 10 minutes, but they couldn't wait 30 minutes. So through algorithmic development, we were able to apply the inertial solution in this case that without those algorithms wouldn't meet the requirements. The next challenging environment that I'm going to address is a slowly moving platform. So here we have an aerostat. These are sort of balloons that hover over environments. They have sensors on them, and they're looking for intelligence, surveillance, and reconnaissance applications for various things in the environment. But the need for having the sensor pointing or geopointing is very important in this application. Now, in this case, we do have enough room on the platform to have a fairly large antenna separation, so the dual antenna or interferometry-based solution is applicable. But there's some limitations to it, and I'll talk about those in a minute. The problem with an inertial solution here is that the platform does not move very fast. It's sort of being buffeted a little bit by breeze and things like that. And so an inertial solution by itself may not provide you the accuracy because of the low level of dynamics that are at play here. So the plot that I show here, I've got a red, green, and blue plots. The blue plot is the GPS dual antenna approach. And what you see there is you get an instantaneous convergence. In other words, there's no need for a filter to converge. You're actually doing direct measurements. And so you get a very accurate heading immediately after turning the system on. But what you see a little bit later on, about 3/4 of the way through the run, you start getting some bad points, and that could be because of occlusions to the satellites or airframe masking and things like that that cause bad points to creep in. The inertial solution is the green solution there, and you can see that that doesn't give you an accurate heading immediately. There's actually convergence time that has to occur, and so you have a problem because the system takes some time to converge. And so what we've done to address this problem is we've developed what we call the Geo-HNav. This is a hybrid navigation solution. It actually takes the best of both the dual antenna pointing and the inertial pointing and combines them into a single solution. And what you see is in the red, you have the instantaneous convergence due to the dual GPS, but you have you're able to smooth through the bad data points because you have the inertial solution to fall back on. So this is our approach to a slowly moving platform. Now we're going to focus on direct georeferencing. Remember that the geopointing is a core functionality that leads us to be able to do direct georeferencing. So direct georeferencing uses geopointing. It also uses positioning and, as Lasse talked about, kinematic processing, dual frequency GPS. I'm not going to address that aspect of it, but suffices to say that that's necessary. So we have attitude and position that go into the direct georeferencing algorithms. And we combine that with passive and active vision sensors. In our case, a laser scanner, a LiDAR, and also cameras. And we directly georeference those sensor data to provide us the ability to do mobile mapping, as we heard in the last presentation. So direct georeferencing of LiDAR point clouds. This is similar to what we saw. We have a UAV that's carrying a mobile mapping platform. It flies over, in this case, a monument that we have here in San Diego called Mount Soledad. And the laser scanner provides us very dense point clouds. And using the geopointing information that we get out of our geopointing capability, we're able to directly georeference those point clouds and provide very accurate coordinates for each of the points in the point cloud. And here's another scan, laser scan. These are actually raw sensor data that we provided. We didn't render them, so that's why they're not in color. But you can see that the accuracies that we get out of the system are a function of the quality of the IMU, whether we're using MEMS or fiber optic gyro or ring laser gyro IMUs, and also the type of GPS processing that we do, kinematic, real-time kinematic, or autonomous WAS solutions. So all of those parameters are added to the error model, and we're able to achieve the accuracies that you see as a function of the sensor quality. The same thing applies to directly georeferencing image data. In this case, we took an off-the-shelf 6mm non-metric camera, a very low quality camera, and we went to the same monument and used the camera to capture some images. And we used our bundle adjustment and sequential alignment algorithms to see what we could get in post-mission and real time. Assuming that we have very accurate pointing data from our pointing capabilities, we're now able to directly georeference also the images. And here you can see how that's done. So as a summary, our goal is providing a high-level capability for things like GPS-denied navigation and the like. We call that environment perception. Those capabilities are built up of lower-level capabilities like direct georeferencing, which in turn is built on geopointing. We address the geopointing capability and how we optimize our algorithms to address cases where an approach of a GPS, dual GPS, or IMU in and of themselves are not applicable. And we can address those either with the algorithms or with a hybrid approach. And then we show that once you have the geopointing information, you're able to directly georeference LiDAR data, camera data, to provide very accurate point cloud coordinates or image coordinates. And from there, you build up the higher level capabilities that you see here. I'd like to invite you to visit us at the ION conference coming up, where we have a paper to present even more capabilities that we're working on here. And the references that I mentioned at the beginning of the talk are here. I also invite you to go ahead and take a look at these papers if you're interested in more levels of detail of any of the topics that we talked about. And I'd like to thank you for attending, and you're welcome to visit us at geodetics.com. And with that, I'll turn it back over to Alan.
All right, thank you, Jeff. We're now at approximately the midpoint of our webinar. I want to let everybody know that we can go a little bit past the top of the hour. We are going to turn to your questions in the last portion of it. We now turn to Florent Hennart from Airbus in France to talk about his work and his team's work in fusing GNSS and vision in UAV design, build, and test. Florent?
Thank you, Alan. And thank you for the presenters before me for their excellent presentations. I'm going to talk a bit about designing autonomous systems. As you can see, I work at space systems inside Airbus Defense and Space. So what I'm used to do is designing navigation for autonomous systems, and we came to work on UAVs as well. So let me explain to you a bit how it went. So 15 years ago, we started working on autonomous navigation solutions for space probes. We're landing on Mars, on the Moon. And we needed an autonomous navigation, no GPS, of course, and no control from a man. And so we developed some solutions based on some sensors. As you will see, it's mostly based on cameras because it doesn't require much power. It's quite light, and we've made some ground demonstrations after that. And what is as common as a probe is a UAV. So we made some demonstration on UAVs, and know that we've seen that on UAVs it works quite well. We also propose our technology on for UAVs. So I'm going to try to share some lessons we've learned during this process. So first, let me show you a bit how we designed our navigation solution that is quite fitted for UAVs. It's based on a camera. We usually use one camera. You can also use two for stereo vision, but for navigation we use only one. And the concept is quite common. You can find it quite easily on literature. It's called visual odometry. And we believe it's a good backup to GNSS for short GNSS outages. So at first it was designed for landing on Mars. So we really had a big work on having a good feature extraction of the images, of the Martian and Moon images that works on all kind of images. It's quite a tricky part to do, but there is a lot of work being done on this matter since a couple of years. And so basically what you do when you do this kind of navigation is looking at how the images, the things in the images move, and from the movement you observe, you can observe a bit of your movement. So you can't observe all the degrees of liberty, and you get only sort of a part of your movement. So you need an IMU to complete the navigation. So what we've done is really this only vision and IMU navigation, and we wanted to demonstrate that it works quite well, and I'm going to show some pictures afterwards. It does work quite well, and then we thought, yeah, why not put it on UAVs and have it as a backup for GNSS. We also use some quite common features that you can find based on absolute navigation. So the good thing with the previous one, the odometry, is that you don't need a map, a reference map, but with absolute navigation, you get an absolute correction of your position. So it's also quite a complementary sensor, kind of, sensor that is. It works very well, especially at high altitudes. It's the kind of algorithm you can find, I guess, on the web, and also that we use on georeferencing or for satellite data. So having both those technologies in mind, we came to this reflection of about how to design a robust navigation chain for UAVs, actually. So when you have a GPS, a GNSS, you quite often have this integrity, robustness, and resilience issues, and we address them through sensor hybridization And what is very nice with an IMU and a camera is that the failure modes are completely different from GNSS. You don't have all this radio frequency part, and you can quite easily make an estimation of the integrity that has the IMU plus vision itself, and then you have GNSS integrity, and you can fusion both. So it's kind of a really nice feature to have both, and both being quite on the same level of performance. So let me show this. Yeah. So when you make a global hybridization of GNSS and vision-based navigation, you can improve the global performance because well, for example, with an AMU, you can sense the short-term noise of GNSS. With relative vision, you can sense noise that is a bit more correlated in time, like multipass or ionosphere variation. You can kind of estimate all those errors, and with absolute vision, you also can estimate all the biases that are inside GNSS measurements. So it's when everything works well, it's very complementary. And when you have an issue with one of the sensors, the other one is a good backup. So we made some demonstrations on that. Let me show you a first demonstration. It took place 5 years ago. It was on a UAV at first, and quite a big one. And at that time, if you remember, the miniaturization of PCBs and so on was not that easy and was not that common. So it was quite a huge system. And actually, it was not designed as a UAV, but as a planetary landing test facility. That's what the PLGTF stands for. And so it was the first demonstration of the fact that the vision-based navigation with the right algorithms can provide the functionality of autonomous landing and estimation of the distance to the ground without any active sensor. Quite often you use radio frequency altimeters that are quite tricky to use. They are quite noisy with biases, and when you fly over water, well, it doesn't happen that often on Mars, but when you fly over water, then usually you get some echoes, and it's quite nice to have this totally different source of information from the vision that gives you quite a good estimate of your distance to the ground. And that is done only by IMU and vision. Another lesson learned is when you design some algorithms on vision, you have to have raw data. So what you see here is not a UAV, obviously, but for a good testing and good design, you need to have a lot of raw data. And the easiest way at that time we found was to put some recorder on board a helicopter and just make a lot of records and just process a lot of data. And you always discover more, you learn a lot more on your technology when you have a lot of data to process. You have kind of a scale effect of all the things that may happen afterwards after you design it. The same philosophy, we performed many flights on a UAV quite a few years afterwards, 2 years ago, I think. So we designed with our partners at Novadem. We designed a platform just for recording, but we've made many recordings on with visual camera, infrared cameras. We also had many other sensors just to have a good estimate on the performances we can get on various flights and various conditions, with rain, with fog also, and so many situations. And so finally we came to real-time demonstration. That was the obvious goal. And so we've carried the technology in the odometry technology, what we call the ultra-fast SLAM, on board a UAV. And we could make the demonstration of navigation without GNSS. So basically what we did is replace the navigation function that was in the UAV that was only based on GNSS with our vision-based navigation plus GNSS. And we made some GNSS outages like you may have downtown in GNSS denied environments. And it was quite a fluent flight. We had no transition between GNSS and GNSS denied instance. And it opens the door to many missions like autonomous surveillance, area mapping, or also the terrain hugging capability thanks to the altitude estimation by the camera. So I think it's, to conclude, it's just very nice to have this vision-based navigation that is very good redundancy to GNSS when you have some issues quite often downtown in GNSS denied environments. So that concludes my presentation, and back to you, Alan.
Thank you, Florent. We turn now to Jan van Hees from Septentrio, who's going to talk about GNSS for mapping without ground control points. Jan?
Thank you, Alan, and good morning or afternoon or evening to all of you. For those who don't know Septentrio, allow me to quickly introduce ourselves. We're a company based in Belgium. We develop high-precision GPS, GNSS receivers and receiver modules that are being integrated for demanding industrial applications such as offshore construction, oil and gas, automation of machine control in mining and construction, GIS, mobile mapping, survey, reference stations and scientific receivers, as well as some applications in aerospace and defense. As Alan told us, the webinar is mostly about the equipment on the UAVs and how to construct that, and less on the mapping process. But I'd like to start with a little bit on the mapping process nevertheless, and specifically it was mentioned before, the traditional process still used quite a bit relies on ground control points for the actual building of the and mapping activity. Now, ground control points, as many of you probably know, are fixed features, in the area to be surveyed, which are surveyed manually by a surveyor to obtain accurate position. These could either be existing features or artificial indications, as in the picture above. The disadvantage of this process is obvious. If you have to access the area to measure a number of points manually, that is a quite labor-intensive and possibly expensive process. It's also a process that can possibly be dangerous in environments, construction or mining environments, or even impossible if you cannot access the area. So, as some previous speakers have alluded to, as an approach to solving that problem, some people, and that includes us as well, put high-precision RTK receivers in the UAV to get to an accurate position for each of the images being taken. Now, apart from giving each image an accurate position reference, the advantage is also that it increases the reliability of the stitching process when the images are being combined together. And in fact, it also can significantly speed up the stitching process when that information is available. Now, the disadvantage of using RTK is that a constant real-time data stream is required between a fixed station on the ground and the UAV. And this telecom link proves to be unreliable quite often. And the mapping process obviously depends critically on the link, so this is a problem in this approach. So for that reason, at Septentrio we've developed what we call RPK, or reprocessed kinematic, whereby you can eliminate the link between a fixed station and the UAV, and still produce with the software that we've developed called Geotags, still produce centimeter accurate georeferencing of the images. The next slide is an illustration of the type of results that you can get with this kind of flying. This is obviously a mapping of a quarry. The image was provided to us courtesy C Astral, who is one of our customers integrating our receivers. And they are reaching accuracies on the order of a few centimeters on the ground, which is similar to other older mapping techniques or techniques using ground control points. An interesting additional aspect with using high precision GPS on the UAV for mapping or for georeferencing the images is that it also aids the stitching process in situations like this one, where some areas of the pictures may have few distinguishing features or a lot of image noise. Let me turn back now to the topic of integrating a high-end GNSS receiver. So as was mentioned probably before, for the type of process that I've just described, the simpler single frequency GPS receivers that are used typically for the navigation of UAVs are not good enough for this process. And for this reason, Septentrio, amongst others, have developed a dedicated receiver that we call Asterix MUAS. Our Asterix MUAS is a compact, low power receiver developed specifically for integration on mapping UAVs. And of course, there's a couple of issues that are important to tackle. Power is an obvious one, so this board is developed to consume as little power as possible, around half a watt. Another important element not to forget is that not only you need a dual frequency receiver, but also the antenna needs to be a dual frequency antenna. A point that requires special attention in this whole chain is the camera shutter synchronization. It's obvious if your UAV is flying at, say, 10 meters per second, that a bad synchronization between the camera and the GPS can lead to errors which would be larger than the centimeter errors that you're trying to achieve on the ground. Now this poses a problem, especially because many of the cameras used on UAVs are, certainly the cheaper models, are rolling shutter cameras, which don't have a very well defined moment of taking the picture, as the picture is built up in steps, if you want. The best approach for that we recommend is to connect to the flash signal, if that's available or possible. Or even better is not to use rolling shutter cameras, because apart from the synchronization issues, in fact they exhibit quite a bit of motion blur because of the technique that is used in creating the image. And a real shutter camera is of course better for that. Another problem to tackle is the data logging. The images on the pictures are typically directly logged onto a flash card in the camera, so that's not accessible for the GPS receiver to log the positions. So on this product, and we've provided in the integration of a flash card that can be easily removed for writing the data of the GPS receiver. But actually the most complicated and important part of the integration is the interference that we see quite often on these platforms. In fact, as some of you may know, GPS signals, GNSS signals, are quite weak signals as received on the ground. Special processing techniques have to be used to extract them from the background noise. And it turns out that UAVs, especially small mapping UAVs, contain quite a bit of noisy equipment that is packed into a small volume. We've got often electromotors and motor control, which create quite a bit of digital noise, but also the autopilot and especially also the cameras turn out to generate quite some noise. The two pictures you can see here were generated with the tools that we develop and provide with our receivers to assist in the integration and troubleshooting during the integration. And they show the signal levels of the different satellites being received, in this case with a GoPro camera with the GPS receiver right on top of it. So on the left-hand side, for instance, you can see signal dips every 5 seconds each time when a picture is taken and some high volume data is being written, which generates the digital noise. In the other picture you can see when the camera is switched on, the signal level drops. When video recording starts, the signal level drops some more, and the signals are recovered again when the systems are turned off. So in fact, this type of we've developed a number of techniques for interference mitigation, but the type of noise exhibited by these systems is quite wideband and stochastic and very difficult to eliminate. Luckily, it turns out that this type of interference acts on a fairly short distance. Now, I realize you don't have a lot of space in a UAV to put things far apart, but actually moving them a little bit apart often helps, and being smart about where you place the different parts of the antenna. And of course, shielding of the electronics is an important element in that as well. Putting a ground plane or a metal foil underneath the antenna is very good practice for eliminating not only this type of digital noise, but also other reflections which can impact the accuracy of the GPS signals received, the routing of the antenna cable, and then in general shielding of the different offensive parts of the electronics if those are diagnosed. Now, luckily enough, we found that simple measures, just like, for instance, using aluminum tape in the right places, can do the job. So the shielding itself doesn't have to be very thick or add a lot of weight to the design. So to come to a conclusion, I don't think anybody here doubts that UAVs are excellent tools for aerial mapping. Centimeter level accuracy can be reached by using dual frequency receivers on the platform. They allow for taking images at a fraction of the traditional aerial survey costs. We've proposed a number of approaches to simplify the process called reprocessed kinematic to reduce also the risk of loss of data. But in any case, when you're integrating this type of systems, it's important to take a number of good design measures to avoid especially the problem of interference. And with that, I conclude my talk and I hand over back to Alan.
All right, thank you very much, Jan. We have we're going to go a little bit past the hour. I have several questions lined up for our speakers. The first one is, you can't, well, my preamble to the first question is, you can't talk about GNSS or GPS anymore these days without also talking about jamming. So far we've focused on getting the platform up and working and flying, and now how do you, to our panelists, how do you plan to protect your UAV from GPS and video signal jamming? Florent, you signaled me that you have some answers on this, so why don't you go first, and then anybody else who wants to jump in can do so afterwards.
Oh yeah, thanks, Alan. Yeah, so on GPS jamming, for me the solution is just find a resilient solution. So yeah, be resilient. I mean, find another solution, other sensors, because you can never be resistant to any kind of level of jamming. So just find another solution. Our solution is vision-based, but you can find many other solutions, I guess. And the question was also on video signal jamming. I guess the video signal can be jammed if it goes over the air, but inside a design, I don't think it's quite easy to jam a video signal. And if you can, I mean, you just send so much power on the UAV that you can almost burn it, I guess. So, and just to comment also also on what Jan just said. You must really care about the jamming that you can make yourself when designing your UAV. We also experienced some, we had some surprises with some USB plugs that were jamming the GNSS. So the design itself must really care about internal jamming.
Yeah, I'd like to add to that. Obviously, I already touched on it during my talk. What we see is these systems are often built from components that have not been co-designed, which requires the type of measures that I mentioned, but which are I'm not going to say easy to overcome, but with good engineering practice and awareness of the fact where you have to start looking for this, it's not impossible to solve. Of course, high-level intentional jamming. I mean, yes, GPS, as was just said also by Florent, GPS, but the whole UAV is vulnerable. I mean, you can shoot at it and it will also come down. So at some point, you can't protect against jamming. But Septentrio has done quite a bit of work on integrating features on the receivers that have both on the RF and the digital side adaptive digital filtering to make the systems much more robust than the original broadband designs of the GPS receivers or GNSS receiver of a generation ago. So there are quite a bit of possibilities to eliminate, especially certain forms of intentional jamming, including chirp jamming. And we've demonstrated in some other talks, including at ION, what can be done against them. So it is not as bad a problem as it's sometimes made out to be.
All right, thank you. Anyone else on that question before I move to the second one? Okay. Our second question, I'll combine two questions from two different listeners. One wants to know what is the approximate timeline for battery-powered flight on your various platforms. And someone else is very interested in continuous UAV operation and wants to know if using solar panels on the UAV to charge the batteries is a practical solution. I'll throw that open to anyone who wants to answer.
I could probably say something about our experience with a octocopter. I don't have much experience with fixed-wing UAVs because they probably fly much longer. But our octocopter just flies with a weight of 5 kilograms. It has like 10 minutes flight time, but it's not optimized at all. So if you take care and everything is very light, and then you may come to longer times, like 20 minutes or something. But I'm not sure if there's much more possible. I don't think that you can go with UAV panels on solar panels. Sorry, with solar panels on the wings. Or maybe you can with fixed wing. Okay, because you don't need much power in this case. So it may be an option for fixed wings.
Actually, there was a solution designed a couple of years ago of a solar panel flying UAV, but that was a very high altitude flying UAV that was supposed to be almost continuously flying, and so that the dynamics and the losses are completely different from the type of UAVs we've been talking about. But it has been built UAVs or platforms that fly with solar panels.
I may add that my company is also building that kind of non-stop flying UAVs. I think mine is called the Zephyr, but many people from big companies are trying to, like Google, are trying to do that kind of stuff also. But if you want to have that continuous operation of UAVs, you may turn to balloons and that kind of half balloons, half UAVs designs that are really quite fitted for continuous UAV operations that most of the time doesn't require you to move that much, but just to hover over some areas.
All right, thank you. We're at the top of the hour, or nearly there, but I'm going to go a little bit past to fit in at least one more question. One listener wants to know or states that UAVs need robust PNT solutions, obviously. We've been talking about this. Rugged to any type of environment, including radio frequency interference and signal shadowing. This listener would like to know if any of you have investigated the use of pseudolights, GNSS pseudolights, as help for professional grade UAVs under such conditions.
No, let me chip into that. No, we have not. It depends, of course, on what causes the shadowing, whether a pseudolight can help. I'm assuming that the idea here is that the pseudolight transmits a signal in the same area or in the same signals bands as the GNSS signals, which it's not allowed in many circumstances, certainly not outside, unless you've got a very, very specific environment. So RF jamming probably cannot be overcome by using that kind of pseudolights. Of course, if you use other transmitters to do a multilateration type of approach in completely different bands, that's a different question, but it makes the UAV way more, because you'll need actually a separate type of receiver system as well then. In terms of flying in shadowed environments, at least for the mapping environments that we've been looking at most of the time, the UAV, of course, being up in the air, isn't usually suffering too much from shadowing, and there's quite a number of satellites available, and the number of satellites is growing as well. So that is not the biggest problem to address at this stage.
Thank you. Yeah.
Just add,
go ahead.
One thing. Yeah, just as Jan said, using pseudolights is quite a problem when you have, because of the regulation and the restrictions. Usually, and what we did for some tests is you can use ultra wideband pseudolights actually, or beacons, and which gives you quite a good positioning, but you have to do all the calibration process, so it may be quite heavy depending on your applications.
It also forfeits the purpose a little bit, in the sense that mapping, the nice thing about mapping with UAVs is that you do not need access to the area, or very minimal access to the area. Of course, if you have to start putting beacons around and georeference the beacons very accurately in order to get your relative position with the beacons into an absolute position for the mapping process, for instance, then that you don't really gain too much. But that's a generic statement, of course. I'm sure you can invent or you can think of specific environment, like maybe a mine, where you could leave those transmitters in place for a long time and use them. But then again, you've got also the range problem and the signal strength problem as well, depending on the area you're trying to cover. So, nice thing about GPS signals is they're available, they're free, and they're everywhere. So, it requires a quite specific situation to need to justify something else in this kind of fairly open environments.
Thank you. Our final question: how long can your platform operate at a reasonable level of accuracy for your mission, and obviously with some sort of navigation? How long can you operate without GNSS? How much of an interruption to the signal can you tolerate?
If I may step on this one. So what we did is not really focus on one carrier, but just on the technology. And so the question is how long, but I would say how far can you stay without GNSS? Because the matter with vision is more about how far you went, or how much features you've seen going through your camera. So the reasonable performance that you will find in literature or in documents is something like 1% of the distance you've traveled, or if you do it well, it can be half a percent. So it's like 5 meters per kilometers, and that's mostly on the horizontal plane. So if you don't have much constraint on where you have to, on where you want to be, then you can fly till your batteries are empty. I guess you can fly. We found 10 minutes without GNSS, and you can fly. You just slowly drift.
Thank you, Florent. Anyone else want to chime in on that question before I conclude our webinar? Oh, all right. Well, I want to thank all our panelists, Lasse Klingbeil from the University of Bonn, Jeff Fayman from Geodetics, Florent Hennart from Airbus, and Jan van Hees from Septentrio. I'd like to thank the audience for tuning in. We had quite a good attendance, and judging from the questions that were submitted, quite a high level of knowledge of attendance. We did not have time to get all the questions answered, but it's quite possible that we may do so in an upcoming print issue of the magazine or in one of our email newsletters. And to access any of those, go to gpsworld.com/subscribe. And forward the link to this webinar to friends and colleagues who you think may be interested. It will be available for download subsequently, so anyone who missed our live presentation will be able to get the full contents. And Jeff Fayman from Geodetics provided some links to some conference papers that are in the slides for further details. Also, if you'd like to read more about Lasse Klingbeil's project, it is the cover story of the November issue of GPS World. Finally, I'd like to thank our sponsor, Spectracom, for making this webinar possible. And with that, I'll turn it back to our producer, Kelly.
Thanks, Alan. Thank you all for attending today's webinar. If you have any more questions, don't hesitate to contact our presenters at the email addresses on your screen now. Links to their email addresses are in their bios as well. An on-demand recording of today's webinar will be emailed to you tomorrow afternoon and will be available online for a full year at gpsworld.com/webinars. If you would like to download today's slides, click to open the green folder icon on the far right of the dock at the bottom of your screen. Our next webinar, Introduction to Using UAVs for Mapping, is scheduled for Thursday, December 17th. If you requested to be included in that event while registering for this webinar, you will automatically receive an email from us. If not, check gpsworld.com/webinars for more information. Thank you, and see you next month.